Hello again, psychology students. Today's video, we are talking about correlational studies. And so a correlational study tells you what it is right from the title of it. So if we take the word correlation and we break it apart to where those double R's are, we're going to end up with something that is co-related, as in we are looking at relationships when we're talking about correlations. And so when we are talking about correlational studies, we define these as the type of study that measures the strength of a consistent relationship between two variables. So once again, it measures the strength of a consistent relationship between two variables. So this is really, really good for making predictions. So we can start to predict if one variable starts to move in a certain direction. Well, typically that happens where another variable is also moving that direction. One of the catches that we're going to speak of several times in this video is even though we can use correlations to predict motion of variables, it can never be proven, it can never prove a cause that one variable is causing the change in another. And that's not to say that it's impossible that it's happening. It just says that correlations have no way of making that statement. And so all correlations say is these two things happen together. And so we can have two different types of correlations. You can have a positive correlation or a negative correlation. And we'll show you how these work as we proceed through this video. But basically, a positive correlation, also known as a direct correlation, has both variables moving together. So as one's going up, the other's going up. As one's going down, the other variable's also going down. The negative correlation is sometimes easier to even think of as the inverse correlation. One variable is going to go up while the other one goes down. And so as one example of how we can start to see these things work out, let's say we have this tree full of berries and we can see it as blossoming and there are lots and lots of berries on this tree. But then we add a bird, and as that new variable, once we add the bird, there's probably fewer berries in that tree. What if we add a whole lot of birds? We throw 1,000 birds towards this tree. We're probably going to be able to predict that there's going to be fewer berries on that tree. And so what we see is the more birds, the fewer berries. You can also reverse that. The fewer birds, more berries. And so that just shows the birds and the berries are variables that are related to each other. So the way we measure these and the way we can start to determine how strong these relationships are and whether something is positive or negative, we use a scatter plot. And so the way the scatter plots work is real world has a whole lot of data points. We're not dealing with just a single point. We are dealing with a wide variety of points. And so as we are working with this wide variety of data points, we know that real world is not always so fancy. And so let's just do a really easy example here. And let's say on my x-axis, one variable is just going to do the hours I have spent studying. And so I'm just going to draw very sloppily with my mouse. So that's hours I spend studying. And one of the things that might be related to that is GPA. Now I'm not using actual data here. We're just going hypothetical here to make the point. So let's say I have that student who studies for hours. They get done with school every day. They go study another 6 hours. That includes weekends. That includes even right after they finish the test, they're going to go study some more. And so that student is really big on the x-axis. So lots and lots of hours of studying. But as we can imagine, that student probably has a really high GPA too. And so if we raise that high on the x-axis and high on the y-axis, we're going to end up with that ugly red bullet point to represent that student. And just so I don't need to do that so ugly again, I'm going to change this up for my next one. And we're going to use highlighter marks instead. So then we have another student. Let's say you're more average type of honor student. They're going to put in a lot of hours of studying. Maybe not every weekend, maybe not every single night, but they're going to also be very high on this x-axis, and their GPA is also probably going to be pretty high. So we'll mark them over here. And then you have the student who maybe doesn't study very often. There's a test coming up, so they'll look over their notes a little bit. They'll use the in-class time when it's given to them. And so maybe their GPA isn't quite as high as that student who's always studying. Then you have the student who never studies, not even in class. Teacher asks them to do a warm-up. They won't even do the warm-up because that might be studying. And so we're going to give them a good solid 0 hours. And they're going to get some credit somewhere, but not as much. And so now we have our data points that represent that variable for 4 different students. So ultimately, just like you would do in math class, we'll draw our line of best fit. And we can tell by looking at this line of best fit, that's a positive slope. And so when you have a positive slope, it means it's a positive correlation or a direct correlation. You can reverse this also. So for example, we could see our birds and berries example. And I'll go really quickly through this one also. If we say this is the birds on the x-axis, sorry for that sloppiness, and we'll just abbreviate BR for berries. We had a whole lot of birds. We saw that there was not very many berries. So that's a very low on our y-axis, very high on our x-axis. In that time in between, we had a medium amount of birds, a medium amount of berries. But before the birds showed up, we had a whole lot of berries. And so once again, if we draw that line of best fit, we end up with a negative slope, which means that's showing us a negative correlation because one variable went up while the other one went down. So if we look ahead at how this might manifest itself, here's some real world types of examples. So real world, they don't always line up in a straight line. That's just, data doesn't work that nicely, but they do help us visualize the correlation. So hopefully as you're looking at this screen, you're seeing that the correlation on the left is a pretty strong positive correlation, whereas the one on the right is a pretty strong negative correlation. And the way we can see that is those dots are fairly close together and they're moving upwards as positive versus moving downwards in our negative slope. Sometimes we end up with data that looks more like this. And when we look like this, there's still a little bit of a positive slope to that data, but it's not nearly as strong. The data points are scattered all over the place. So that tells us, well, that's a much weaker correlation. Those two things aren't nearly as related as they were on the previous slide. But we need a more specific way to measure this. And so when we are talking about measuring correlations, we use this data we call the correlation coefficient. So when you are looking at studies, this is often printed as the R value. Now you should know already, R stands for relationship. So a correlation coefficient statistically measures the strength of a relationship. So once again, it statistically measures the strength of a relationship. And so we use that R value and we give it a number between -1 and +1, and that will tell us how strong that correlation is. So as you can see on both of these lines at the bottom, if we start with a +1, every single dot lines up perfectly. We call that a perfect relationship. So for every time variable 1 moves up 1 notch, variable 2 is going to move up the same amount. And so we see that moving up perfectly in sync with each other, and you end up with a perfectly straight line connecting those dots together. Now in the real world, that doesn't happen very often, but it shows you what a perfect correlation means. And so we would write that as plus 0.1. The plus refers to it being a positive correlation. The 1.0 refers to it being perfect. On the other hand, we can move to the left side of this and we can have a -1 correlation. And again, we have a straight line, it's just moving in the opposite direction. It is still absolutely perfect. It's just a perfect negative instead of a perfect positive. So -1 and +1 are both considered perfect. Now I'm going to warn you of a type of question that shows up a lot on tests, and both the ones I give as well as the AP exam. Very often they'll throw out a bunch of numbers and say, hey, which one of these shows the strongest correlation? And maybe they will have, we'll say, we'll put one here at positive 0.5. We'll put another one really close to 0 over here, and we'll call it a -0.1. It's a -0.1. That's a positive 0.5. And then they're going to give you a negative 0.8. And then they're going to give you like a +2. And hopefully that threw up some red flags for you. Because +2 can't be right. Because it's beyond perfect. This line ends at 1 and it ends at -1. You can't be more perfect than perfect. And so when you look at a +1, how could you be more perfect than everything lining up perfectly? And so that +2 can't possibly work because it just mathematically is not a way we measure correlations. And so that one's automatically wrong. But then we still have 3 other options. We can see in the middle here, there's no relationship. No matter what, we can't find a relationship. And so if we're close to 0 and I'm asking you what's the strongest relationship, it can't be the one that's really close to 0. But sometimes that positive and negative throw students off. And so what we always want to look at is which one is closer to the 1. And it doesn't matter if it's positive or -1. And so if we ask which one's strongest of these 4 values on the screen, -0.8 would be your strongest because it's the closest to perfection, or it's the furthest away from 0, which is also showing us that no relationship at all. And so real world, we end up with decimal marks. And so real world, while it would be great if we could say there's a +1, let's say, for example, in a real classroom, for every student that walks into my classroom, I will have 1 homework assignment that's turned into that tray. Now that would, if perfect correlation means every student walks in, every single student turns in an assignment. In reality, it doesn't always happen that way. Now, I really hope there's a 0, as in I can't predict anything about students coming in numbers. But what we know is maybe that 1 student forgot to do it. Maybe that 1 student is going to do it, but something came up last night. And so while 20 students walk in the room, I only get 17 assignments turned in. And if that becomes an often thing, now we could say, well, it's a very strong positive correlation. More students mean more homework turned in. But in the real world, it's not perfect. And that's the case with nearly all real world data, is it's hard to find perfection. Especially for my AP students, I just wanted to give you a couple other examples of how these correlation scatter plots could work with the correlational coefficient. So you can see the 3 you've already seen with no relationship and perfection. But you can also see now here approximate 0.6 or approximate -0.6, just to show you there's still a relationship. We can still find the line, but it doesn't happen perfectly every time. As we discussed in our previous video about scientific thinking, correlational studies have one of the biggest moles that seem to just never die. And so it's critical for you to understand this big problem with correlations and kill it so you never fall into this trap. And you will hear it, and it's going to sound natural when you start to hear it, when people start to make the same mistake over and over and over again. But the biggest mole is that people confuse a correlation with one variable causing another. And it's easy to do because we see these variables move together, so one has to cause the other. But we didn't measure that. So if you ever hear a study that comes on, and I've heard this on real news reports before, a new correlational study says that texting while driving causes more accidents. And here's the problem. Does texting while driving cause accidents? It's very possible. But if that's a correlational study, it didn't say that. What the correlational study said is the more text messages sent by a driver, the more accidents they are in. And so there's a big difference from saying these 2 things happen together than one caused the other. So I'm going to have you, while you're sitting at home, I'm going to have you do the same thing I would have you do in class. And it's going to feel a little weird because you're at home, but I promise you, everyone else in your class is chanting along with you. So I'm going to bring this next slide up, and I need you to read the entire slide. So as you can see here, correlation does not equal causation. That is the big thing to take away, and I need you to read the whole slide, and I need you to own it every single time. Drive that into your brain. I'll sit here and wait while you read the entire slide. Own it. Say it louder. Did that go into your head? That correlation does not equal causation. If it didn't, rewind the video, do it again, and keep repeating it until you know that the word relationship and the word cause never go together when we're talking about psychological research. So let's look at where this can get, let's drive home the fact that we don't know cause. So here is a real world correlation, and you can see the R value there in the middle of your screen is a 0.947. So basically these two variables are 95% related. How much cheese is consumed in the United States and the number of people who died being tangled in their bed sheets. This is a real correlation. There is a 95% rate of these two variables moving together. And so more people die in their bed sheets, more people eat cheese. More people eat cheese, more people die in their bed sheets. Now, what the temptation is for us to go in and start looking for causes. So if you eat cheese, are you likely to get tangled up in your bed sheets? Or does getting tangled up in your bed sheets cause your family to go buy lots of cheese? And we can't do that. All this says is they move together. We don't know what causes that. There could be a whole bunch of things, or it could just be a random connection. Here's another great example of this. And again, look at the power of this correlation. From 2000 to 2009, there is a 0.99 strength of the correlation between the divorce rate in Maine and the per capita consumption of margarine. So as fewer people get divorced, fewer people consume margarine. And so when we look at these things, we can't find cause. We just have to say there's some weird things out there. I did include a website in our course resources of a whole bunch of these, and it's called Spurious Correlations. It's where I got these two, and there's tons more of them that are just fun to go and look at to say, hey, these two things are related. And we want you to keep in mind these two things are related does not mean that two things are causing each other or that they have anything to do with each other other than the variables move together. I'm going to have you do one more practice as we wrap up today. So as you can see here, I have two new variables. I have ice cream sales in millions and shark attacks, and this is real world data. So what I would like you to do with this for practice is make a scatter plot, determine is the scatter plot or is the correlation between ice cream sales and shark attacks, is there one? If there is one, is it positive or negative? Give it a rough correlational coefficient. Don't do any math. Just if it's really strong, give it a really high number. If it's really low, give it a really low number. Make sure you pay attention to that positive or negative at the beginning. And come up with our answer. Does ice cream cause shark attacks? And if not, tell me why they are related. So go ahead and pause the video and complete this as best as you can. And then we'll work out how we should have approached this. So go ahead and hit pause now. So your scatter plot should look something like this one. And I didn't try to do anything really perfect here, but I made each dash here represent 5 on the data that was given. So we can see the really, really high one here. We have 20 and 20. I'm sorry, 37 and 25. The really low ones, we have our 50 and our 20. And then what we try to do is we look at the scatter plot, and if it helps, we can draw that line of best fit and see how close are these things to the line. And so what you should have seen here is you should have seen a pretty strong positive correlation. So students will usually measure this somewhere between positive 0.6 and positive 0.8. If you're in that range, you're right on. I don't have the exact number to calculate that either. But if you label this as a strong correlation, you're right. Your scatter plot hopefully looked a little bit like mine in that case too. So then we have to look at, so what does this tell us about the relationship of ice cream and shark attacks? And all it says is they're going to move together. We cannot determine cause because all we gave you was correlational data. What we can say is ice cream sales are going up. I can make a prediction that shark attacks might be going up and vice versa because it does allow us to predict the movement together. This is a great example because a lot of people will start to look for those causes and realize how weird they are. So shark attacks start happening because people smell like ice cream, or people celebrate shark attacks by going to buy ice cream. None of it makes sense. What does make sense sometimes is that there's an extra variable that has an influence on both. And so very often there's another variable that's more of a causal factor than this one. And so in this case, as we study these, the extra variable that we should consider is temperature. Because as temperature goes up, people buy more ice cream. And that makes a more logical connection. It's hot outside, more people want ice cream. It's cold outside, fewer people want ice cream. And of course, some people are going to buy ice cream no matter what the temperature is. But the sales increase a lot when it's hot outside. Shark attacks also increase when it's hot outside because no shark can attack if there's no one swimming in the water. So if it's really cold, people choose not to go swimming, so there's no one in the water for the sharks to attack. Those temperatures start going up, and all of a sudden, then that opens up a possibility for that to happen. And so maybe what we can often try to do is identify what else could influence these variables that would make them also move together, even though they're not directly causing one another to move. So that closes out our video on correlations. What we should have taken out is this is a great way to measure relationships. It's a way to predict movement of variables, but it can never show a cause. And to close out with the proper drilling into your brain once again, I'm going to stop the video with you chanting correlation does not equal causation. So go ahead and continue on with that chant to really drive that into your brain.